All right, so wait a second, let's remove this.
Did you prepare a small teaser like shirt and
Ruhe. All right, so today we're going to look into a solution for the problem of last time. If you remember, we're trying to have basically jobs distributed to a worker and then have some lock on a central resource that needs to be written by a writer and read by all the workers, but in parallel, right? We don't want to put the workers in sequential order when they access, for example, a matrix to do their computation. So that is not achievable with the normal lock, with a semaphore, or with anything that you can find in the multiprocessing library. So today we're going to see how we can actually create a reader-writer lock in Python using these basic tools that we have at our disposal. And to do that, we first need to understand how can we lock a resource with, let's say, participating processes. So all the processes share the same lock. And basically, the first one locks it, and the last one out release it, right? And that's what light switches, and we'll see how it's implemented. The basic idea is that you have a process coming in, and it does not acquire the lock directly, it acquires this switch. The switch itself keeps an internal counter. When the counter is 1, it acquires the lock. When the counter is greater than 1, it doesn't do anything. And when a process releases the switch, it decreases the counter. And when the counter is 0, then it releases the locks as well, right? So this way, I'm sharing this lock among all the processes. Now, if I'm doing this, of course, I can have like 30 workers coming in using the matrix that I'm sharing in a shared memory. And they will all be able to read it at the same time because they all share the same lock. But when the writer wants to come in and write to the matrix, I don't want to acquire the light switch. I want to acquire the lock, right? So then the writer will be blocked until the last of the reader has finished reading, right? So and that's the basic concept that we have. So this is basically how we're going to implement the read-write lock. So you have basically 2 ways to acquire the read-write lock. One is the reader acquire, and one is the writer acquire. The reader acquire interacts with the light switch, while the writer acquire interacts directly with the lock, right? And that's basically then hidden inside my reader-writer lock. And yeah, it should basically work, right? So any questions about the concept? How are we going to implement this? Reader, writer, right? So might be boring for some of you people, but let's see what the implementation looks like. So let's first look at the switch implementation. So not swish, not swish, switch. The switch implementation has basically 2 elements: the counter, and I need the lock. Why do I need a lock inside? Can anybody tell me why I need a lock inside the read-write lock? I mean, I am passing the lock. I want to lock or unlock, right? Through the acquire, just to make it more flexible. But I need an internal lock. Why do I need it?
Because
the code and explain me what I'm doing basically. Why do I need that lock?
The counter increment in line 13 is not atomic.
The counter, because the counter is shared. So if I'm increasing it and checking, I want to make sure that this stuff is atomic, right? So I need a lock to lock that operation. And that doesn't have to be transparent to the outside. It's an internal thing that I'm doing, right? So this is important. Whenever you deal with the internal variables that are shared across different processes, you want to make sure that if you do something like this, increase and check, that you don't do it without the lock, because otherwise you can increase, check, right? Process 1 increase, process 2 increase, process 1 checks, process 2 checks, it's never 1. It starts with 2, right? And then it doesn't work. right? So, but besides that, it's pretty simple, right? I go into acquire, I acquire my internal lock, I increase the counter, check the counter is 1. If it's 1, I acquire the shared lock that I need, right? And then I release it again. To release, I do the same. I just acquire the internal lock, decrease it, check if it's 0, release the internal lock if it's 0, only if it's 0, and then release my, sorry, the pass lock, and then release the internal lock. And then I just add a helper function to report the counter, because again, remember what is double underscores? It's a private variable. It basically scrambles the name of the variable so that you cannot access it, like underscore underscore count. All right, so I just did a little demos to see if it works, right? So I'm just starting a function from 1 to 5. I acquire the resource 5 times, and then I release it 5 times. I'm just printing the count every time and sleeping 0.2 seconds. And when I'm starting this, so I start this use resource in a different process. P-start, I sleep half a second to give it a chance to start, right? But this is not yet over. This is full second, right? Full 2 seconds, actually. And then I try to acquire the lock while this guy goes through his reading phase, basically. So what do I expect? What should the print out of this if I run it? What do you expect? So I'm at the process start. What is the first thing I should see? Can write or discount? What happens first? The counter, right? I mean, you might say, okay, if the process start takes more than 0.5 seconds, it might be actually the can write, but it usually should take less than that. And then I should see first this counter. And then what happens? When does the can write appear? Until the last one is released. Why? But until this 4 is over, right? Why?
It's locked.
Because of the counter. Because resource is locked until the counter is 0, right? So we start with counter increasing here because we put the sleep here, and then keeps increasing, so it never has a chance to acquire the resource. And then until the last one releases it, it doesn't have the chance, so it will wait until 0, then print and write, and then join the process, and then we're done. Shall we run it? See if our intuition is correct. Right. And yeah, wrong order. Let's try this one. So since we were correct, right? So it's incrementing, printing 1, 2, 3, 4, 5, arrives there, then it's decreasing 4, 3, 2, 1, 0, and then we can actually acquire in the main process the lock and done. So seems okay, right? Anything that we should change in this implementation? What do you think? Looks okay to you?
One question.
Yeah.
Starting the process would take longer than the sleep time we have. Then we would be in a deadlock because we would acquire the resource. And
well, because I don't release it, we would be in a deadlock, right? I mean, actually, this should be something like resource. Yeah. I mean, release. Yeah. Well, it's not completing it for me. All right. So yeah, that's actually correct. I should always release my logs. Yeah, but otherwise it seems fine, right? Mm-hmm. Okay, so let's move on and see what the implementation of the lock itself should look like. Right. So So I just copied over the light switch. I'm also putting some incrementing, locking incremented so that we can follow what's happening, right? And the same decrementing, releasing decremented. And now the read write lock. I have my switch, I have my reader lock. So what am I doing here? Basically, I want to keep a lock around so that the writer can lock it directly and the reader can actually increase it through a switch, right? That's basically the main concept. So I'm just masking what we did before in the main, now in these 4 meters: reader acquire, writer release, and reader release. So the reader acquire just increments the switch, and it locks only on the first time. The reader release decrements it, and if it's the last one, it releases it, while the writer directly acquire and release the lock. Makes sense, right? All right. So then let's look at a simple test. So the reader, my process reader, which I would start 2 of them, right, are going to acquire the lock first, reading something and sleeping. Then once they're done, they're going to release the lock. How are they doing it? Through the switch. So okay, counter base, right? While so the writer, which is implemented in the main thread, what will it do? Will sleep 500 milliseconds, then try to acquire the lock with the writer acquired, can write, release as before, and then we join. Make sense? Any question on this? And then this is pretty much the same as before. We just introduced a new class, and we're starting 2 processes instead of 1.
Could you scroll up a bit?
Yes. Shall we test it? And give me a second. I don't think we can do this like this. Damn it. Okay. I hope you can read then. So I'm reading it for you. Incrementing 0, locking 1, incremented 1. Good. Reading, process 1. Incrementing 0, locking 1. Done. Process 1. And now we're stuck. What did just happen? So remember, incrementing 0 is basically when it acquires the internal lock. It tells me I'm incrementing, then it increases the counter and checks if the counter is 1, then it's printing locking, it's locking the lock that I passed it, and then it prints incremented when it's released. So it's doing incrementing 0, locking 1, incremented 1, what we expect, right? Then it says reading process 1, which is printed. Where was it printed? Here. So after I get the read write lock, I'm printing reading, waiting for a time, then I'm printing done, and then I'm releasing the reader write lock, right? So reading and then done. Okay, this comes from these 2 guys. In the meantime, I have another incrementing 0, locking 1, coming apparently from a different process. What happened? Any ideas? Where did we go wrong? We did go wrong somewhere, right? We are in a deadlock. So where are, let's start with something simple. Where are these objects? the light switch, where is it initialized? Where is it in memory? We have three processes, right? The main process, the first worker, the second worker. What we do is we start the processes. Let me go back to this view.
Do we need to use a singleton? That we just have one? No.
Can't, right? It's different process, different interpreter. So even if you use a singleton, it's going to be a different object. So we start the process. The process is starting this reader and passing along this object lock. Okay, so a reader is this function here. The lock is basically passed along here. What happens to this lock when I pass it?
Oh, processing different objects, something like that.
It is shareable.
It's what?
Shareable.
So
It's not the same lock object. So you copy a new one to each of the new processes.
don't be fooled by the word lock. This is not a lock from multiprocessing. This is a class that I defined. It's an object like any other object. So what happens to an object when I pass it to a different process?
It's a reference.
It's not a reference. It gets what? It gets serialized, marshaled, what do you want to call it? It gets saved to memory as a piece of bytes, you know, a stream of bytes, and then it gets unmarshaled in the new process, right? So what happens to its fields? If I increment the fields of the original count, if increment the original counter in the original process, does it increment also the one that I share with the new process? No, of course not, right? So that's where it went wrong, because I initialized my counter inside the switch, which is a field in the lock at 0. I passed it along, that created a second counter in the first process, a third counter in the second process. And then when I incremented the counter on the first process, second process doesn't know nothing about that, right? It's clear. So be careful whenever you pass an object. I mean, if you call it lock, it doesn't mean that it's ready to be shared. You still need to go through the thought process of saying, okay, what is really important that is shared across the processes and as a shared memory. And then you have to make sure that it actually is so, because otherwise it doesn't work, right? So let's see how we can solve this problem. And maybe we should stop the execution here. All right, so what we want to do is have a bit more infrastructure here. So when you acquire, you don't want just to pass the lock, you want to acquire. The lock is fine, this can be shared, it can be, I mean, the real MP lock, right? Multiprocessing lock, that can be shared, it can be cross-processed, that's its job. But for the counter, you need actually to have initialized some shared memory that you need to share across all your switches, right? And what you want to do is, when you do this, use the shared memory interface. For example, in this case, I just, further on, you would see, I just allocated 1 byte, because I don't think I'll have more than 255 readers, okay? So with 1 byte, I can just increment the buffer there by 1, check if the buffer is 1, and then do my process and release. And here you can just decrement it and check if this is equal to 0, right? So that's pretty easy. The rest of the interface is the same. And when I actually initialize the stuff, I just create my counter like this. So create shared memory, I give it one size, create true, and I assign 0 to it, initialize it to 0, right? Pretty easy, right? Then I create my lock, and I start the processes by passing both the lock and the counter. Then in the read-write lock, my reader acquire and my reader release, they need to have a reference to the counter, so that I can increment it and decrement it using the same memory address for all of the processes. Does it make sense?
Could you please show the code again from the counter where you increase the shared memory?
Sure. So this is the light switch, right? So now when I want to acquire the light switch, I want to pass it the lock as well as the shared memory for the counter. So then I go on, I acquire my internal lock so that I'm doing this atomically. more important because now I have a shared memory. I mean, before it didn't matter because it was each one had its own variable, but it didn't work, right? So in this case, it's actually important. I increment the buffer, then I check if the buffer is one, the shared memory counter.
You
Then
don't need another log for increasing the shared memory. That's done internally. So when you add something here to the counter to the shared,
that's my lock, right? To do this. This is always atomic. The lock here, it's okay because it's an MP lock. I can share it across processes. That's fine. If I define any other, basic type, I couldn't. But an MP lock I can share across processes.
because it's not the switch log. It's just like
Yeah. This is not a class I define. This is something that is basically implemented by multiprocessors. So it's fine to be shared. So I lock it here. Then I increment my shared counter. Then I check my shared counter. So all this is atomic. If it's shared, I acquire the main lock, and then I release the internal lock, and then I'm done. Okay, then I'm out of the acquisition phase, and I can read all I want. When I'm done, I'm going to release, and I'm decreasing my shared counter and making sure that, the contract is respected, that the last one out releases the lock.
Since the code grows more and more, there any prebuilt libraries you could use?
I didn't find anything. I looked for, I didn't find anything that has reader writer locks implemented. Found this implementation. I mean, there's many implementation. I found one that was a bit more complex than this. I simplified it because I mean, the point is you can make this a lot more fancy, right? And we'll see a few things that you can do with the reader writer lock later on today. But usually the standard thing is that you have one writer and multiple readers, and you don't care about things like a multiple writer accessing the resources at the same time or things like that. But there is a few things that you can do, and this involves then multiple switches, multiple locks internally, and we could see that part of it today. Okay, so if you're interested, I can show you the full-fledged reader writer lock next time, but it's a very complex. Let's move on. Okay, so this should do the job, right? Any weakness you see in this implementation? Anything that could happen? What could happen here that can make my life hard? Say I have multiple readers, really a lot of them. They acquire the lock, start reading, release the lock. And then basically, after a little while, acquire again, start reading, release it again. Okay, now if the writer coming in wants to write something, will they get a chance? No, right? So unless you have a scheduled sequence, like the writer is also in charge of giving the jobs to the readers to do, and then at some point it stops giving them, so the reader has to stop. The writer will never get a chance to read, to write anything, because this counter will always be made greater than 0, right? So this is a problem that this implementation has, and we'll see a different implementation that solves this. And there are other problems when you implement that. We'll discuss it later. But again, this is not the perfect reader write lock implementation. It's just something that will get through the day if you have a sequential scheduling and you just want the readers to go parallel within a certain block. But the writer controls when they stop, progressing with their schedule. And then it starts again after you wrote everything. So shall we test it, and then we can look at how we can solve our last time problem using this implementation? Oops. All right, so let's run this. I mean, that's what we expected, right? Now it's everything is working fine. I'm incrementing 0, locking, incremented 1, reading process, incrementing one, incremented two, so it's not locking here, right? Because it's the second one around. Reading process two, done process one. Again, they are reading parallelly, right? I don't care about the lock, so it's not sequential. Done process one, decremented two, decremented one, done process two. Also important, the done is after they incremented and after I basically finish with acquiring things. So this is important because I'm acquiring this internal lock really in and doing the counting, and then I'm starting to read, right? Because if I were to do this, I would basically implement a sequential order, right? So this is why it's done like that, and it's important. And you cannot implement this sequence with the simple lock, because otherwise, if you try to, you get basically a sequential order of the readers. So this is all fine as we expected. And the end is decrementing and releasing and decremented to 0, and then it can write. And the writer can get this job done, right? Any questions about this? Does it all make sense?
I guess to be really sure, we should also move the print statements above into the log, into the log. Right? If you scroll up a bit.
Oh yeah, because they could be also out of.
Because it's shared memory. I mean, it probably doesn't have to.
Yeah, I mean, the point is you would like to have this inside so that it's not out of order. Yeah, that's okay. Yeah, but I mean, the point is it's doing what it's supposed to do. So let's move to the problem of last time. Do you remember? We have this nice problem with workers that are basically, while the event is going on, checking the queue if it's empty, otherwise leave. And if it's not empty, then they're doing some operations using a shared matrix, right? This guy over here. And doing a multiplication, and then they're releasing the log. And this was, last time when we implemented, sequential. The reason it was sequential is because we had to use this shared memory during the multiplication, because we don't want to copy it again, right? And at the same time, so we have to protect it with a lock. And since we have to protect it with a lock, it's sequential. So now we can finally implement it with a read-write lock. And the code is the same, except for my read-write lock, this update lock is here. And it's doing, the job now through a counter, so we can do this parallel. Any question about this? Right, so the implementation is quite simple, right? The main, I mean, the sync doesn't do anything. The main two processes are the worker, which we just see, and the ventilator. The ventilator takes two arguments. One is the shared memory where we put down matrix for the multiplication. The other one is the counter that we want to pass it so that we have a common counter for all the readers. And and the same goes for the counter, for the worker, sorry, we have filter and a counter, plus stop event, ventilator queue, and so on, all the usual things from last time. So what we do here is we initialize, let me see. So here, we initialize our shared memory, remember that? You basically create an array here, then you initialize the shared memory, checking how long the array is, and then you copy the content of the array into the shared memory, and that's basically your shared memory right there with the content of the NumPy array. You can read it in the same way by just reinitializing it like this and passing it the buffer of the shared memory that you pass to the other process. And this is going to use the same underlying memory in both processes. So you don't have to worry about copying it in or out. It's very quick. I mean, it's just zero time because you're just initializing the light structure on top of an existing memory. So you're not moving anything. Right. So then I initialize my processes. I pass it my update lock, which is now a read-write lock. Okay, I pass my counter, which is share from the external process, right? And then I'm initializing, starting all of them, and then I go into the main process of the of my ventilator, which is checking if the queue is empty. So it basically so once every update filter every, right? Once every 10, in this case, steps, it tries to update the matrix. In the other cases, it just waits until the queue is full and put otherwise a new job to be processed, right? So basically fills the queue with jobs to be done by the workers. If the queue is filled already, it waits and keeps filling until it reaches update filter every, which is 10 in this case. Once it reaches 10, then it tries to update the kernel matrix. And it does that by using our read-write lock. So it acquires the lock, it copies the content of a new randomly generated matrix into the shared memory, and then it releases the lock. So in this case, it does a writer acquire, a writer release. So no reader will have access to the shared memory at all in this case, right? Clear so far? So, and then the main process, I just generate the two shared memory. I create the ventilator process and I start it because I'm creating the worker process inside the ventilator. So I don't want to start, don't have to start them here, just start the ventilator process. Any question about the code before we start running it? In this case, the ventilator takes care that everything is done before it updates. So this acquire is not waiting for anybody, right? Because all the workers are done. So I'm not running into the problem of starving the writer because the readers are always active. If I didn't have this, if I had actually two processes completely independent, then I would run into that. But this is not the case because I'm counting how many workers, how many jobs did the worker do before I update, and then I'm waiting for them to be done. Do I need to wait? What do you think? So what happens if I remove this guy? Let's go through the code mentally. First time around, I go through the for loop. I'm at 0, so this is doesn't kick in, right? I'm here. The queue is not filled, so I put a new matrix inside, and then I'm at 1. This doesn't kick in again. Kicks only in at 10. So I'm at 2. The queue is still open because the queue, I think I put it at 5, all right? Queue is still open, so I put the second job in, and I move in again. Put the third, the fourth, the fifth, until the queue is filled. At the 6th, I don't know, am I sleeping or not? Did the workers already process the first item already? Got it from the queue? Might be, right? I'm gonna wait at some point, like at 7, 8, I don't know. At some point, the queue is going to be again, it's going to have again 1 slot free. I'm gonna put the last job. Now I'm 10. I go through this. I don't have this check. What happens here? Anybody wants to speculate?
But we don't know the size of it. We want to put in more.
No, the filter is always the same size. I'm just initializing another random 4x4 as before. So just copying the content inside. Will I be able to acquire this lock?
Battery 100%.
So as long as there's at least one vector reading, then no.
Exactly. So as long as there's one reader that is active, this lock is going to be not possible to acquire from me, right? So most probably, what will happen?
Most probably we are stuck with right of player or blocked waiting.
So exactly, because it's very improbable that all the readers are, done with their current job at the same time. They all release it, so I can acquire it, go and write before the next reader comes in and gets the next job, right? So it's very improbable that I am actually doing this before the 10 jobs are done, right? But it's not impossible. So I have no guarantee that actually I'm updating this after 10 jobs. I'm only updating it not later than 10 jobs, but it could be 9, 8, 7, I don't know, depending on how many readers I have, depending on how long it takes for them to do the reading and how long it takes for them to switch between finish one job and acquire the next. All these things is basically then it's a random number generator, okay? Between 5 and 10. Most probably biased towards the 10, right? So that's basically what it is. I don't have a guarantee. If I wait for the queue to be empty, then I have a guarantee because I know that all the workers have got, that basically the last job is now in a worker and it's being processed. And until all the process are done, I cannot acquire this log. So they will be done with the 10 that I put in before I actually update the central field, right? Everybody agree on that?
I'm just thinking, don't we need to move the while loop before the if statement, so like outside there? So like you start the process until your queue is empty, and then you check if like 10 were processed. But doesn't make a difference.
You would
Maybe I
do
just,
put this up here
yes, exactly.
and then the if in here,
And the time sleep also there.
the time slip as well.
Yeah, the whole while loop. I mean, and then moving that part below that.
Like this,
Yes.
but
Only the state.
only the ifs. Yeah, sorry.
Yes.
Sorry about that.
Then you would wait.
I mean, then you would wait until the queue is empty, and then you
Okay.
check.
Past 0.
Okay, maybe, yeah. But I mean, the thing is, when you check inside of the if statement, it could still be that you check you are at 10, and then you wait until the rest is done. So it would still be possible that there was one process processing, and it would increase to 11. You just wait for it.
No.
Not?
No. Okay, the I is just the enumerator of the source.
Mhm.
Okay, the I doesn't change. If I'm inside the loop, it doesn't change. It's fixed, right? Every pass because it's coming from here. So the reader doesn't increment it. All right.
Okay.
So every 10 elements in my source is file, JSON, whatever it is. Okay, it's a list of images.
But I mean, if you have 11 problems, for example.
Yeah, I stop at 10, right? I stop.
At 10, yeah?
Let's. I mean, this doesn't work, right? Is it obvious that this doesn't work?
Yeah, I mean, yes, sure.
Okay, so let's move back to the original.
I think it would work, right? It just would wait for
For the complete
it should wait at
Has-
every problem.
Okay, so the while, I'm not switching it again, right?
Yeah,
The while outside, past 0, is the queue empty or not?
but you can press zero.
So is the queue, when I have the first element, I is equal to 0. So the queue is empty or not?
Yeah, it's empty.
It's empty. So while not empty,
Yeah,
it's fine. Okay, I'm going to, but then I put one in,
yeah.
and then if the reader was not fast enough, I'm stuck. I'm waiting for no, I'm not stuck. I mean, the reader would pick one, and only when it picked one, I put the next.
That's what I'm saying. So we would wait for every problem, for all the workers to be finished. So
Yes, so it's basically, I'm basically keeping a queue of length one.
exactly.
I'm forcing the queue to be of length one. And when I'm getting inside so the while is outside now, when I'm getting in the if filter is equal 10, right? Well, then basically I will get the first chance. So it's like what we did before. So basically what we'll do, it's going to be sequentialize the writing and the reading, right? I will not be able to keep a buffer. So it will be less efficient, and we actually were. And I will not have a guarantee that I'm actually processing 10 before going to the 11th. All right, thank you.
The length of source is 10 now.
The length of source is 100.
It's 100. Okay. Okay.
So the source is here.
Okay.
It's just an iterator that goes through 100 items and pushes always a random matrix. And I initialize it with, where is it? Source. Oh, come on. Here. So I initialize it this way. And no, 30. 100 was too long. Yeah. So it goes through 3 cycles. Right? So, everything else is clear? Shall we run it? What do we expect? It's a good idea to, when you're writing multiprocessing, to have your intuition, think about what you expect, and then see if you actually seeing what you expected. Because rationalizing the results is easier. So what will be the first thing that we see? We have here a print when I start computing and a print when I'm done. And then we have this update filter updated print. So what should be the sequence that I'm seeing here? First the updates, how many? This one here is 10, right?
First update goes to 0.
Mhm.
Then you do some computing.
So the first update is 0. Then the updated comes right after because I have a lock. So this is atomic. Then I am computing, right? 10 of them. Then I should see update 10 and so on and so forth, right? And it should be always 10 computed in between each update. And the update should always be atomic. There shouldn't be any reader overlapping with the update, right? That's important. So let's try to run it. All right, so updated 0, computing done, computing done, updated 10, computing, and so on. Okay, so it does what it advertises. It finishes all the processes before it actually goes and updates the matrix, and then it starts, and these are now in parallel. These are not like last time that they are sequential. I can actually parallelize my computation because I'm using this reader writer lock. Right? So it does what we needed to do. We move on. You happy with this, or should we? So then, if I manage to open this guy, for whatever reason, you know. Seriously?
Click on project.
I think it's stuck on the side for some reason. Seriously? Okay. We'll do it like this. All right. So the problem of the writer starving, how do we solve it? Anybody has an idea? I mean, first of all, let's test the writer starving, what it really is, right? So here I'm doing something slightly different than before. I have a reader, locks my resource with a read write a lock, reading time sleep done, and reader release. I have a writer that it's basically starting all my processes and then going to a round of 100 times where it tries to acquire the writer lock and printing writing and then releasing, right? So according to our intuition, these guys should actually start my writer. The writer should not be able to print writing before all the readers are done. Does it make sense? Let's see if I can run it now. Yeah, it works. Look at that. Run. All right. I mean, it's pretty small, but you see that there's no writer writing, right? So reading done, reading done, reading done. So the writer actually doesn't have a chance. How do we solve this? Anybody has an idea?
Some kind of shared flag that prevents readers from from acquiring the log again if the writer requests or something like this.
So you're suggesting we do what? Sorry.
When the writer wants to acquire the log, just set some kind of flag, some notification. So I want to have the log, and the readers then cannot acquire the log again.
What's such a flag called?
A log.
Yeah. So we can use a lock to sequentialize the access to our switch as well as to our resource. How will we do that? Right, we don't want to sequentialize the readers. If we put a lock directly here and release the lock here, we are sequentializing the readers. So all this is for nothing. We can just use a simple lock. We're done. So how can we do this without sequentializing the readers? See if we get to the solution without me showing your solution first. So where do we want to queue them? At the acquisition, right? It's important that first come, first serve at the acquisition phase. So I want definitely to put a lock here, right? Some lock my queue, my sequence, whatever that is, basically another lock. And I also want to lock here. So that they're now they are queued, right? They're all waiting for the same lock. But these do not have to be sequentialized. So what do I have to do here so that they're not sequentialized? First reader comes in, it locks my queue lock, okay? And then it acquires the counter-based switch. And then the second reader comes in and it's stuck.
So the first one shouldn't lock the lock, So just check if it can look. So, or just immediately release it.
Better idea, right? So if I immediately release it here, release, then the next one will come in, will be able to acquire the switch-based lock, not to switch, and then release, the Q lock. But if the writer comes in and locks it, then they are stuck, right? So until then, this basically, well, no reader is going to be here waiting, because they always acquire the switch, which can always do, and release immediately the lock. So the one that is next in line is going to be the writer, always, right? Does that make sense? Yes.
Why couldn't it be like that the only one who can like the thing Lucas said was like the writer is the only one who can like set the flag or lock the lock to 1, and the others just check. So no lock release, just check and wait.
Just the second lock, like a writer lock, and like in the reader,
Like
you
so to say,
only
the reader only reads the lock and the writer actually writes.
I
the lock.
understand the concept, but we need to implement it. How do you propose we implement it?
So
We have a lock. We have semaphores, which you didn't see, but basically they're locks with counters. What else do we have? How can we implement this?
So there is no lock that is acquiring the. Okay.
You can try to acquire it. It's a atomic action, and you can release it. That's it.
Okay.
So how would you implement this, right? I mean, this is a simple implementation. It does basically the same concept, but instead of checking, it actually does the acquisition, does its stuff, and then releases its stuff right away. So in here, then I have basically, I can queuing up all the readers behind the writer. When I acquire here, because I am not acquiring the switch, I'm acquiring directly the internal lock, right? This is going to be blocked by the switch until the last reader gets out. When the last reader gets out, I am actually going through this. I'm not releasing it because I don't care. Why? Right? Then I have to release it here. All right. Does that make sense?
It does also sequentialize the readers again.
Does not. How does it sequentialize the readers?
Because we release the lock out. Oh no, it's just acquired. So, okay. Yeah.
Why release, right? They are not sequentialized because
I thought the brackets.
what is sequentialized is the acquisition of the switch itself.
Yeah.
But this is anyway sequentialized because I have my internal lock protecting this method all the time. So this is atomic.
Yeah.
But what I'm saying is, don't you see something wrong with this?
It can be like, if possible, the writer always acquiring lock, always releasing, always, and then the readers cannot acquire the lock.
No. This works. Trust my word for now, this works, right? But is it too complex? Can I simplify it? Can you see a possible simplification point here? Acquire lock 1, acquire lock 2, release lock 2, release lock 1. Can we use this reader lock to actually do this operation? We can't. Cannot be simplified, right? Because if you try to do this, then you will never be able to acquire it because there's probably some reader right there. So no, you actually need this double locking. Right? So these are two different locks and you need them both. But it's always a good idea to think about when you're implementing something like this, do I actually need this? Can I simplify this? Can I use the same lock for both stuff? But no. And the way you want to debug it is by conceptually going through the phase and see what's locked, what is not. Better even do it on paper and check, process 1 locks this, process 2 locks this, what happened? Can I go on? Can I not go on? When go scenario based. Anyway, no, I need this lock, I need this release because otherwise it doesn't work. So because I'm nice, I already written all this stuff. And actually, I did a little bit of optimization here because I don't need to keep the reader queue acquired. Once I acquire my principal log, I'm done. So I always rather release it early than later if it's not needed, right? That's the only difference. The rest is the same. So whenever I acquire, I first acquire the reader queue, then I do my log or switch acquire, and then I release the reader queue. Same goes here.
The difference is that you're using the reader queue now.
Right, exactly. So I have an extra lock, which I call the reader queue. And basically I am queuing up this acquisition here, right? And then I'm queuing up then with the writer acquire as well. So it's a common queue. Everyone tries to acquire it. The readers, they go through their switch, release it immediately. The writer, since it acquires the lock, it blocks the queue for everybody because they cannot get the reader. Then we have to wait for him to get this. And then I can release the queue because anyway, they will not get past this. Because they're gonna, if I release the queue, the first reader in the queue will acquire the queue and will try to wait on the switch. And the switch is not being able to give it to them because this is blocked, right? It's going to try internally to acquire the lock again, increasing the counter, try to acquire the lock, and the lock is already acquired by the writer, so it needs to wait for this.
If there would be functions is acquired, you could remove those two lines around the switch acquired. So you could just check for the if statement, see if there is the flag set or not.
The is acquired is a very bad idea. Why?
Because I check first and then do the stuff and if you could get acquired.
Exactly. Checking if something is acquired is never a good idea because you have to make sure that it's atomic. So you have to actually acquire another lock to check if that lock is acquired. How does that make sense? The best idea is actually to try to acquire it directly, right? Yeah, otherwise you go on
I get
infinite loop.
I mean, but the idea from it to
Yeah.
just check if there's like a lock or not, and then do like depending on that a specific action.
Right. So what you could do, and you'll find it, is you can actually implement two switch, right? One for the reader, one for the writer, and start doing some interesting checks. Let's see who's waiting, who's not waiting, and based on how many people are waiting on one side, how many people are waiting on the other, I could decide to, give precedence to one or give precedence to the other. This you could do. You could basically implement a counter in your queue, right? It's a bit more complicated. You would not going also because the time is up. We're not going to go through anything of that sort, but you can do it. You can have a lot of fun with these kind of things. You can implement in your own intelligent load balancer for processes, right? Because you can create an internal structure, you can increment counters, you can check, you can put logic. So possible, right? You have the basic tools to do it. This is just a very simple example. Right. Should we run it? I mean, just to see that it works. All right. So now you see it gets actually the chance to write now and then. It's trying to barge in, it's trying to acquire the lock, the queue kicks in, blocks of the reader, they get stapled here, done until they are done. The writer kicks in and then they start again. The problem arises with this kind of processes, but we're not going to go through this. The problem arises when you have multiple writers. What happens is that if you try to implement this with multiple writer, you actually sequentializing most of the readers. Because basically by acquiring the queue, they separate readers from readers. You understand, right? I mean, if I have my queue and then I have reader, writer, these three guys will never be able to run in parallel. Because every time I have a writer in the queue, they're going to separate the readers from one another, and they're going to sequentialize. So if the readers are of the order, right, the number of readers of the order of the number of writers, well, the other way around, then probably this implementation is not a good idea. Oh, now it's going through writings because I had more writings than readings. Is that clear? And there you would actually want to implement a couple of switch and some logic to give precedence to readers in case, basically you have two different queues. Block it with a switch on both sides so that, I can accumulate readers on one side, accumulate writers on the other side, and then decide based on how many people are waiting, which side to go, right? And this would be a more intelligent way to implement the reader-writer lock if I have this kind of situation. But it's very rare that you have multiple writers updating the same memory block, right? I mean, for our cases. Good. I think that's it for today, and hope you enjoyed it. Stop the recording.